So, as I said, we started last time looking at comfort, and we have several sensory mechanisms like thermal, visual, acoustics, spatial, related to space and social and so on. And if there is a change in temperature, thermal for example. So, sensible heat is through temperature. So, if there is a small change in temperature, that is what we call a stimulus input from the environment. Similarly, change in the loudness level, noise level, right. So, that is loudness level actually, intensity of sound. So, that is again related to, is another kind of stimulus, or a change in the lighting level. So, these are the stimulus. So, you get signals actually, right, and they go, the receptors are eye, ear, etc., they are the receptors, right, and then this goes to the cortex and subcortex for processing, and then it gives a signal whether you are comfortable with it or not. I mean, whether you can tolerate this or whatever it is, your reactions basically. So, mathematically one can talk in terms of 5 I's, which are the stimulus input from environment, and this it goes to the receptor and processing in the cortex and subcortex. So, these are transmitted through nerve cell, right. Okay. So, basically then they go to synapse and nerve cell body to synapse and dendrites and all that. There is a physiological mechanism. It is essentially form of electrical impulses and responses. This is physical part of it. Temperature is physical, physically you can measurable things, but there are issues like adaptability. There are issues like adaptability, you can adapt, and there is also some kind of psychological components also. So, actually response is a function of, response psi is a function of phi 0, and one can phi 0, I mean is psychological part is psi actually, and phi 0 is a response. So, it is a function of phi I, which is a stimulus input. Phi psi is the psychological aspects. I mean, it is associated with your mental feeling of being well-being or not so well-being, that kind of thing. Plus also the environmental factors which you can acclimatize on. It's if a person who's say born and brought up in a, or spend most of their life in, let us say, higher temperature tropical countries, they find cold countries slightly cold intolerable, while this is not so for the people who were brought up there. It is other around, when such people come to, let us say, a tropical scenario, they cannot tolerate higher temperature. So, this is acclimatization and all that. Besides the psychological well-being, that part, that is also there. So, anyway, simple relationship is one of, that is Weber-Fechner's relationship, where it says that delta phi 0 is the response. So, delta d phi 0, which is the response or the smallest response, is a function, is a function of d phi I by phi I. So, it is proportional to d phi I. For example, the least amount of temperature difference, say delta phi I, as I am saying, this one, let us say minimum change in temperature, that you can perceive, that is perceptible, is this is a minimum. I mean, this if below some value of this you won't find anything, d phi 0, there will be no response. So, there is a minimum level, and that is divided by phi I. So supposing there is at higher temperature, because it is divided by, say, at 37 degrees centigrade, if you perceive, let us say, you can find out 0.5 degree change. At 25 degrees centigrade, you will be requiring, like it is proportional to the temperature itself, less temperature change you will be able to perceive, because d phi by phi I is equals to d phi 0. So, this is the response, this is the response, this is the response. So, to minimum perceptible response will depend upon the actual temperature as well as stimuli change. Change in stimuli divided by the value of, for example, temperature value 37 degree. So, let us say this d phi is 1 degree. So, 1 by 37, minimum d phi 0 you need is, let us say, some fixed value, because that is what you can, that is the response. Response may not be in terms of temperature, it is, it's, you can perceive it. So, the temperature difference you require to perceive at higher temperature is more, because it is a ratio of phi I to d phi. Similarly, lux level or visual lux level, the lighting level, which at higher lux level you require more d phi to get same d phi 0, to find out the difference. Visually we can find out the size of object, or let us say something like glare. Glare is related to, again, logarithmically related to the level of contrast and so on. So, this is Weber-Fechner's law. In other words, if you integrate it, you get, if you integrate it, you will get phi 0 minus phi 0, phi 0 1 minus phi 0 2. Let us say this is perceivable, this you can sense, it is a function of log of phi I to 1 or phi I to, it is a function logarithmically related. Change in logarithmic changes, the stimuli inputs is logarithmically related to our perception, right. So, if you change the, let us say, light level, lighting level, so log of some function, let us say some log of some let us say lux level, I mean, since I have not defined, I am not it is difficult for me to at the moment tell you. So, log of the lighting level, let me say, which was there, and you have now increased it. So, log of the second value, log of the increased value minus the log of the first value is related to the kind of perception, whether there is a change or not, whether there is a change or not. I mean, you may not be able to perceive if this difference is too small. If this difference is too small, there is a perception level. There is a minimum difference required for which you will be able to distinguish that there is a change in the lighting level. Now, that is related to log of the initial lighting level minus log of the final lighting level, that is what I am saying. Similarly, you may not be able to sense that there is a temperature change if the environment temperature change. It is related to log of the initial temperature minus log of the changed temperature. So, it is related logarithmically, all right. Similarly, intensity of sound, decibel, as we shall see, it is logarithmically related. Intensity of sound, which is related to loudness, it is logarithmically related. So, some of those things are logarithmically related, and that is this law says. This law says that is logarithmically related, right. So, this law says that is logarithmically related. Now, we can look into thermal comfort. We will come to visual comfort and acoustic comfort, noise related comfort whenever it comes. At the moment now, since we are looking at the thermal aspects, so we will now look into thermal comfort. Now, if I look at thermal comfort, this is a human body, let us say, and I might have radiation coming from outside. If all my surfaces are quite warm or some appliances are there which are hot, they would actually, there will be heat, they will be transmitting heat by radiation. Also, I can lose heat by radiation if the surfaces are cold. So, it depends upon the temperature difference. So, radiation heat loss. Similarly, convection loss as well as gain. If the air temperature is high, then I will have some heat gain, body will gain heat from the surrounding. So, body gains heat or loses heat to the surrounding both by radiation as well as by convection, right. And then conduction loss also can occur through something like, your body is in contact solid with any solid, like I am standing somewhere. So, conduction also loss and gain take place. Now, in addition to this, there is metabolic gain. As I said, whenever you are doing activity, your heart never stops, certain body parts never stop working. So, it is working, heart is pumping all the time, blood circulation is going on all the time. So, you are generating, because all the energy that we gain through our biochemical process from the food, etc., etc., it goes in our locomotion, movement of the blood circulation, all those kind of things. Now everything is not converted into work, it cannot be. Some of it will be lost as heat to the surrounding. That's what we know, that all energy cannot be converted. Thermodynamics tells us that there will be the system cannot be 100% efficient. So a lot of it is lost by as heat, and that depends upon the amount of or nature of the work that you are doing. If your blood circulation increases, loss of heat becomes more. So that's metabolic heat gain to the body. Now this heat is actually absorbed by the body. Finally, it has to lose to the outside environment, otherwise body temperature will go on increasing. So metabolic heat is always a gain. It is always a gain, metabolic heat gain, and it depends upon your activity. There can be loss by evaporation from the skin. There can be loss by evaporation from the skin, because evaporation is always a loss. The body has got a mechanism. What it does is, when temperature, body is not able to dissipate heat by convection, conduction and radiation to the surrounding because it is warm. Then what it will do? It will start actually first increasing the blood circulation at the skin. So that temperature of the skin increases, and if it is higher than the surrounding, then it can now lose some of this heat. If the skin temperature is higher than the surrounding, so more blood circulation, skin temperature increases, and it can then lose some. But supposing this also does not work, because temperature outside is quite high, air temperature just outside the body is quite high, then what it does, it actually starts generating moisture at the skin surface, losing moisture from the body, and this will evaporate. So it is a kind of adiabatic cooling, because when it evaporates, it takes the latent heat of evaporation from the body itself or skin itself. So that's evaporation is always a loss. Besides that, through our respiration process, hot gases will be exalted out from the body. So some loss can also occur, moisture loss as well as both latent and sensible heat loss can be there through respiration process. So perspiration, sweat, etc., all this process can lead to loss. But there is some gain also. I think I have not mentioned it here. There is some gain also in winter. For example, surrounding temperature is very low, then body starts losing heat rapidly, and in the inner body temperature, particularly temperature of the brain, if it goes down, then things it may not be functioning, system may not be working. So you start feeling a kind of discomfort when the temperature outside is very cold, because body is losing heat. Anyway, you can clothes, etc., these are very much there. Besides that, body has got its own mechanism. What it does, it starts generating heat more. Now how does it do? By shivering mechanism. So shivering mechanism is one by which it generates more heat, so that even if the heat is lost, something is being supplied to the body. If you are doing anyway some exercise or something, that would generate heat, but so shivering mechanism is gain of heat, sweating mechanism is for loss of heat, right. So that's what it is. So you can see that deep body temperature is somewhere close to 37, 37.4, etc., right. And if your temperature actually reduces down, or it can reduce it down by evaporation, convection, conduction and radiation, and heat gain can occur by convection, conduction, radiation, shivering, vessels, metabolic activity, the metabolic activity. So this is causes gain, these are causes loss. So these three are common in both the places. Shivering for it causes gain, and this causes. So finally, body should maintain something like 37.4 degrees centigrade, which is deep body temperature. So the body heat, body heat from body core will pass from the skin, so it actually maintain that temperature. So what happens is, when I am looking at warm temperature outside, the temperature is higher. So body heat from the body core would come to the skin, pass from skin if it is exposed, or through the clothes, right, directly to atmosphere, or partly through the clothing to the atmosphere. So through the clothing some heat will be passing, some whichever part of the body is exposed, it will lose heat directly to the atmosphere. So we can actually model it. How do we model it? Assuming conduction heat transfer to the body, or equivalent conduction. deep body temperature. So, this is your body core temperature, there is a QM, right, and then skin temperature is TS, then clothing TC, and then boundary layer, because skin is in contact with air. So, you will have a surface conductance kind of effect, boundary layer. So, one can think in terms of resistances from body coat to the skin, from skin to the clothing, and from clothing to the or clothing or skin to the boundary layer. So, one can write like this: resistances, think in terms of equivalent conductance, and therefore, something similar to U. Transmittance, we can conceive something like this. Sorry? Because the skin is in contact with the air. So, that would be by convection and radiation, like wall surface to the surrounding. We took HOHI, something similar. So, this is the boundary, I mean, it's a very thin layer. We can't define this in absolute length unit because it's not fixed. So, it depends, it's a very thin layer, but temperature of the air is always higher than the surface temperature, solid surface temperature. So, that we have taken it in terms of equivalent convection radiance, equivalent conductance. The radiation and convection we have taken in terms of equivalent conductance. So, we are talking of that resistance 1 by HO or 1 by HI, 1 by HO or 1 by HI, right. I mean, the thickness here shown is a schematic diagram. So, that is why the thicknesses are not really. So, supposing QM is the heat generated, right, there will be some evaporation loss, and let us say the fraction is K, Km is the loss by evaporation, right, because like as I said, through a respiratory system also you lose some heat, and right from the skin you are losing some heat there. Then KQM is what passes. So, loss is 1 minus KQM, sorry, KQM is what passes through the clothing, and some portion goes through the skin and evaporation loss and all that, 1 minus K. So, conduction loss, then the boundary layer loss. So, convection and radiation losses, as I said, boundary layer will have convection and radiation losses, and therefore, this is how you can conceive it, model it in that manner. So, values of metabolic heat dissipated, let us say activity typically given is this, we will come to that model, is Fanger's equation, because you can simply write steady state equation QM passing through that, and sum up 1 by R. So, Q will be equals to all resistances 1 by all resistance or something similar to your U value into delta T, temperature difference, right. So, we will come to that, but typically just to tell you what is the metabolic heat dissipated values are: sleeping and digesting, let us say 47, sitting 59, walking at 4.2 kilometer per hour would be of the order around 154, and there may be many more. Now, clothes are important. So, units of clothing, resistance of one clo, it is called 1 clo. Resistance of the, because the resistance of the cloth is important. This textile engineers apparel design, this is a whole subject in fact. So, they like cotton clothes, a little bit digression. Cotton clothes are very good in the sense that they allow porous, allow a lot of air movement. When polyester or synthetic ones came, pure synthetic is very uncomfortable in warm humid climate, because the losses, evaporation losses are relatively less. So, then came the mixed terracotta, terraline and cotton mix. So, there two things you need, the polyester or similar sort of things, synthetic one, you will have crease, like you press them once, that remains, while cotton the press goes away. So, they know the technology developed. So, they are coming back to it. So, they too use this very much apparel design, and you imagine if this is to be done from armed forces people or people in upper Himalayas or something of that kind, So, this is another complete science behind it, but 1 kilo is 0.155 meter square degree centigrade per watt. Resistance, resistance of clothing we define, and so we call it 1 kilo, 2 kilo, etc., etc. So, unit of clothing resistance is 1 kilo, must be related to the summer clothing in Europe, UK. This must have come from somewhere from there only. So, some are light, some are dress, which will obviously will have a coat also. In European scenario, not like this. An Indian scenario or tropical scenarios, it will be in fact barefoot and things like that. Even bare bodied part of it, like a villager of good old days working plowing, in a field. So the comfort level, even in exposed open field, it could be because they are working hard, working metabolic heat generation could be quite high. Anyway, coming back to this, so unit of clothing resistance is kilo, 1 kilo, and it is 0.155 meter square. So lounge suit with normal inner garments is 1 kilo. That's what I say. Lounge suit. There's a summer. So that's how this unit came, right? Winter clothes could be 2 kilo, and Arctic suits, Antarctica and Arctic suits, fully covered is 4 kilo. So you can get some idea. So heat balance of the body then. QM is the metabolic heat generated. This is the metabolic heat generated minus some losses is equals to the QD that is to be dissipated, and that is to all those mechanisms, some evaporation, some conduction and radiation, convection and all that, right. This is radiation. That can be plus minus, because in general equation is general form we are writing, it could be plus or minus, but finally net has to be, balance has to be there to maintain the inner body temperature. Conduction is plus minus, evaporation is minus, convection and radiation and all that. So area of the normal body is taken like this, it is height is HB and W is the weight, body weight. W is the body weight. Normal body weight is taken as WB, and this is an empirical equation. So surface area of the body through which heat will be lost. It is it's related to the body mass, weight and height, right? And then there is some 2024 meter square. That's it. But effective would be related to cloth also. So some factor for clothing and some factor, area of the clothing, etc. Finally, it is 0.8 N is taken approximately. These are, we don't like just some sort of kind of an empirical values, right. Exact is not really required, because it will vary so much from person to person, or globally if you try to see, it will be very highly varying. So we take it roughly as 0.8 N, through which heat has to be dissipated. So QMD is equals to Q, this is per unit area. I can now divide by per unit area. So QD, if I divide by the area, the heat that is to be dissipated, right, this is to be dissipated is given by this expression. Per unit area, if I divide by 0.8 N, then I get the per unit area. So this QMD should be equals to TB minus TS. What was TB? Body temperature minus skin temperature. Body temperature minus skin temperature. So total, this is the work, actually this is the metabolic heat generated, some of it goes into the work in the body. Finally this is to be dissipated out of the body, right, and this is divided by this area, because flux I am finding out, and flux is proportional to temperature difference divided by resistance, right. So resistance for the skin, now QMD is what has to go out, it comes to the skin this much, then I should multiply by a factor 1 minus K. So KMD is TS minus TC divided by RC. If I recollect the diagram, that I had a resistance of the skin first, then resistance of the clothing, then resistance of the surface boundary layer. So QMD must be equals to KQMD. K is the factor which goes in, and 1 minus K goes out from the skin itself, directly from the skin itself. 1 minus K is going out by evaporation as well as So through the cloth this must be dissipated, KMD it must be dissipated. So, that finally has to be dissipated, and one might actually model this, but such modeling do not help us much really, only except that understanding the heat dissipation occurs through skin, cloth, and clothing is important. So, from this what we are understanding is, I mean there are details of these Fangas equations, but that is just simply this equivalent Q K Q M D is equals to T s minus T c by R c, and that must be also equals to T c minus T a divided by resistance of the boundary layer. So, but it gives us understanding. What understanding does it give? This exercise, the algebraic exercise that I have done. Clothing is important. Your comfort condition depends upon clothing. It depends upon amount of radiation you can receive. Now, where do you get the radiation from? All the surfaces. Supposing I have got a light or something and it is quite warm, light some kind of lamp or something, or some sort of this is light together with some sort of louvers and fitting, this kind of, these are the fitting, light fitting. This may not be as warm as it is it used to be, because good old days, now you use all those LEDs and much less actually heat generation there. So, most of it is light, converted into light. But supposing I have a heater or something of that kind, that would dissipate, that would transmit heat. And surfaces in summer, those who stayed here, let us say in Delhi or northern India, in summer, in an unconditioned room, you go and touch the wall, you will find that it is very hot. If you touch the ceiling directly, suppose in concrete ceiling it is there, you will find roof, you will find it is very hot. That means those walls and surfaces will be radiating heat to your body. Air temperature could be lower, but radiation effect could be there. I am just saying, or air temperature both can be higher. So, therefore, radiation effect is also to be taken into account. This is what two things we have understood from all this exercise. Clothing is important, radiation is important, and obviously air temperature is important. Now, one more thing is important. What is it? Because your body can cool by evaporation, loss heat by evaporation. Therefore, relative humidity, the capacity of the air to absorb moisture, that is also important. So, what we have found out, besides clothing, radiation, that is your surface temperatures, relative humidity, air temperature, these are important things. Now, there can be losses by convection and evaporation, and it could be by forced convection, because we remember we talked about free and forced. Force is related to a velocity of the air. Therefore, radiation of the surfaces, air temperature, relative humidity and air velocity, these are important factors for thermal comfort, because heat can be dissipated through the body like that. Okay. Clothing is important, and adaptability, because if you remember Weber-Fechner's law we are looking at, we said there is a psychological as well as social aspect is there, adaptability is there. So, these are the other factors which goes in defining some sort of thermal comfort or quantifying thermal comfort in some relative terms. So, we will just look into it in a minute or two times.